In this video, we'll pick up where we left off last time in class, where we did an example of determining derivatives by using the difference quotient and taking the limit as h approaches 0. To review the definition of the derivative, it's always as such. We refer to f prime of x to be called the derivative function, and it's always equal to the limit as h approaches 0 of the difference quotient, which, remember, the difference quotient describes the average rate of change of the function between points x and x plus h. And if we take the limit as h approaches 0, we're finding the slope of the curve as those 2 points of the secant line get closer and closer together, which again determines the slope at point x, which is always the point of the reason why we care about f prime of x and why it's so significant in calculus. And as it says down here, when such a limit exists, we always say that the function is differentiable at that point x. And differentiation is just the verb term of derivative noun for doing the same sort of thing. And there's a lot of synonymous things that mean derivative, such as rate of change, speed, velocity. Well, that depends, but we'll talk more about various applications of derivatives as we progress through this lecture series. But let's go ahead and look at some more of the examples from our notes. Starting with f of x is equal to 5x minus 11, it says to find f prime of x and use it to find the slope of the tangent line at various points. So again, let's start with our definition. So f prime of x is always equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. And it's useful to start by thinking about what is f of x plus h by itself, just because that is something we'll have to substitute into our difference quotient. And here it would be, I would have to replace x with x plus h. So remember, the algebra behind f of x plus h always, it means to plug it into the function as an algebraic expression, replace x with x plus h. And, many times I might need to use properties such as the distributive property, but that would give me 5x plus 5h minus 11. And so working on the simplification of the difference quotient, I have the limit as h approaches 0, and f of x plus h is 5x plus 5h minus 11. And then I like to put this in parentheses when I substitute it in, just as a habit, and I've seen many mistakes made with the algebra behind the difference quotient, which is why I recommend doing this. But I also need to take away f of x, the original function. So that needs to be subtracting the original f of x, which is 5x minus 11. Again, notice I use parentheses here around f of x as I substitute that into the difference quotient, because when you're taking away a function, the distributive property will apply, and basically both of the signs here should change. And this is all needs to be divided by h. Now, again, I could simplify this further by using the distributive property. I have limit as h approaches 0 of 5x plus 5h minus 11, and this would be minus 5x plus 11. And as I said in class, and as I'll keep reminding, usually when I'm dealing with polynomials and a lot of algebraic functions, there should be a lot of cancellation among the terms in the numerator of the difference quotient. That's just how it works when you're taking a function and subtracting something very similar. But notice here, I'm going to wind up with, well, 5x minus 5x are like terms. Those will cancel out to make 0. And of course, minus 11 plus 11 also makes 0. So I get a lot of cancellation within the numerator, and that leaves me with the limit as h approaches 0 of 5h over h. And one of you guys asked me in office hours, why do I have to wait to take the limit? But remember that a limit, since division by 0 is undefined, direct substitution is not available. I can't actually apply direct substitution in such cases until it's simplified. In many of the times when it comes to polynomials, rational functions, and so forth, you will get some form of cancellation after you run through the algebra of simplifying. And what I'm left here with is, well, h divided by h is, of course, cancels and makes 1. So this would just leave me with 5. And remember, based on limit law number, I think it was limit law number 0 or limit law number 1, the limit of a constant is always that constant. And even though the limit is as h approaches 0, what we end up with is just a limit of 5. and the limit of 5, regardless of where we're headed towards, is always just going to be 5 because it is a constant value, will not change. Limit does not affect the constant. And so that leaves us with our final answer here of 5. And actually, this is a bit uncommon. Usually derivatives, as in the examples we've looked at so far, are not constants, but are actual functions based on x. But in this case, it just has to do with the original function. So, and again, I'll go ahead and just rewrite this. This is equal to f prime of x. We would refer to this as my derivative function based on the given f of x. And also kind of reworking on going back and looking at our original function here. Since it was a linear function, mx plus b, we know that the slope of a linear function is always based on that constant multiplier out front, or we often call it m. The slope is 5. And remember that that's what a derivative function does. The derivative function tells me the slope. So it should not be surprising that our slope is 5. And basically what this is saying is that the slope of this function is 5 regardless of where I'm at. And we can always look at a graph to sort of confirm that the answer that we're getting makes sense. Because a derivative, again, it does something real. It tells us our slope at point x. And 5x minus 11 has a y-intercept at negative 11 and a slope of 5. And since it's a straight line, it will have the same slope everywhere, which we all know to be 5. In the next video, we'll do a few more examples of calculating derivatives this way, especially when the derivative is not a constant, which is not typical.